I wanted to welcome Geoff Vallis here today. So Geoff got his undergrad at Oxford, then PhD at Imperial College London, and then he went to Scripps for a postdoc. After which he joined the faculty at UC Santa Cruz, and he actually helped start the applied math department there. Then he moved to GFDL in Princeton, and in 2013 started at Exeter, where he has been since, and just finished up as department chair, a 3-year stint that just finished this summer.
Yeah. Yep.
So Geoff is an expert in fluid dynamics, applied mathematics, and atmospheric science. He's a fellow of the APS, and he also has written a very influential book on atmospheric and oceanic fluid dynamics. So it's a great pleasure to have Geoff visit us. And I think he's going to tell us about Rayleigh-Benard convection, or maybe something a little bit more complicated than that. So I guess once we get the last technical details sorted out, I guess Ted needs to be co-host. Great.
Good.
So why don't you take away, Geoff?
Okay, thank you, Daniel. Thank you for inviting me. When we were setting up the applied math department at Santa Cruz, running the applied math department, Northwestern was actually one of the models that we were looking at elsewhere to see how it worked, and decided not to follow that example. No, actually, that was one of the examples that we were trying to follow. It's nice to be here for seminar. Thought that has to be a well-behaved speaker. Feel free to ask me questions as we're going along. So I know that you're still alive. I'm told that you're not all fluid dynamicists, but you may nonetheless have heard of Rayleigh-Benard convection, which is just convection between two plates. You just have a hot plate, cold, and some incompressible fluid between it, and it gets hot and it goes up and down. And that's a very simple model. That's the most widely studied model of convection in the world. I'll show you in a minute. But it may or may not have anything to do with convection in the real world. Advanced. No, it's so advanced. So Rayleigh-Benard convection is convection of an incompressible fluid between two plates. It doesn't have moisture in it. So we add condensation. We add a moisture variable to it, and that rains. So then we have Rainy-Benard convection, which is in fact the title of the paper in JFM. We weren't quite sure whether we could get it that way, but indeed. So apologies to. And this work begun with two colleagues at University of Leeds, Doug Parker and Steve Tobias. I've talked a lot about my early work. Work language a little bit, and it has been picked up recently by a number of people. Chris Howland at 20, and I've been talking to Daniel also about it. And I'm going to also show a little bit of independent work courtesy of Whitney Powers, Ben Brown at CU, and Jeff Oishi. And just a shout out to the software framework Daedalus, which you're probably familiar with here. Wouldn't have been possible, certainly wouldn't have been possible for me to do it without Daedalus. Okay, so if you look at convection, sort of a popularity contest, this is just a random quick search on Google Scholar. If you type in Rayleigh-Benard to Google Scholar, you get 24,000 citation in a fraction of a second to just pop up. If you tap moist convection, don't quite get as many, but you still get a very respectable 17,000 results. If you tap up moist Rayleigh-Benard, 54, not very many. It's not, some other papers of that, Chris Brevetton and a bunch of papers by Olivier Bowlby and Joe Schumacher. You get a few more if you put in moisture plus Rayleigh-Benard. Oftentimes, if you look at the paper there, they'll say, we're going to talk about Rayleigh-Benard. And unlike atmospheric convection, it doesn't have any moisture in it. They'll say, and then they go on to talk about it. So moist Rayleigh-Benard is not very forward. Partly because there are just two communities. There's the atmospheric science community, and there's a sort of applied math and engineering community, or sort of a pure physics community, which look largely at Rayleigh-Benard. And to some degree, never the twain shall meet. So here's just a two-dimensional Rayleigh-Benard, somewhat low Rayleigh number simulation. Cold at the top, warm at the hot at the bottom, cold at the top. And low Rayleigh number, you get the updrafts, which are warm, downdrafts, which are cold. It's up-down symmetric, and that's true of all, true in 3D, true to all Rayleigh numbers, and that's just true by the way that you're setting up the system. It's a boosted fluid, incompressible, and the boundary conditions, you can just flip the whole system. Atmospheric convection is kind of different. It's clouds, and they are manifestly not up-down symmetric. Moisture is coming in, condenses in these clouds, it will rain. So looks very different. Just here's another picture. Again, Rayleigh-Benard on the left, some clouds on the right. And there's a lot of the biggest difference with the atmosphere is that the atmosphere is moist, as I mentioned, and there's a release of latent heat. So when fluid goes up, it condenses, that releases heat, that makes it more unstable, so it may keep on going. So a situation that is stable when it is dry can be unstable when it is moist because of this release of latent heat. And that release of latent heat obviously is something which is occurring internal to the fluid. So we have some internal heating and cooling right in the fluid. Whereas in Rayleigh-Benard convection, all of the heating, all of the buoyancy gain comes in through diffusion at the bottom. And one of the big controversies in Rayleigh-Benard convection is whether you can end up in a so-called ultimate regime, because you can imagine, on the one hand, that all the heat has to come in through diffusion at the bottom. There's no other way to get in. Therefore, the diffusivity must be important. Therefore, let's say it's obvious that molecular diffusion is important. But then if I look out there in the atmosphere, pretty hard to believe that molecular diffusion is actually important in making these clouds. So there's a sort of a controversy in the field about this. Some people will say, oh, obviously, diffusion is always important. Some people say, obviously not important. So let's leave that argument aside for one moment. So here just, well, basically summarizing what I've just said, Rayleigh-Benard is the laser pointer is not too powerful. Who's an S fluid between two plates? There's a basic state with no motion. You can just imagine that it's hot at the bottom, cold at the top, and it diffuses heat from the bottom to the top, and you get a linear profile of temperature. That's called the conductive basic state, and that exists. And it's a very simple solution found by Rayleigh. And then you can do an instability analysis of that by Rayleigh and Chandrasekhar. And generally, you find out for high enough values of the Rayleigh number, that will always be linearly unstable. The transition to turbulence has been well studied. Bifurcations, period doubling. This was one of the prime examples of seeing period doubling and so on in a real system. And there's various theories for the heat transport. The Nusselt number is how much heat is actually transported from bottom to top. The Nusselt number is the ratio of that how much is transported to how much will be transported if it was just a diffusive system. And there's various theories as to how that varies on the Rayleigh number. As I mentioned, sometimes it's thought that heat transport always depends upon molecular properties. Atmospheric convection. It's an ideal gas, it's compressible, there's no upper boundary. The atmosphere just fades away. It's also condensation, liquid water clouds, radiation. The linear theory is not known because the conductive state is not known. Because of the presence of moisture. The transition to turbulence is not known. There's no theory of the heat transport. And as I mentioned, it's believed that the transport does not depend upon the molecular properties. So there's quite a big gap. So what we wanted to do in this study was to take baby steps to go from one to the other. And we're probably staying closer to Rayleigh-Benard than the real world. So if Rayleigh-Benard is here and the real world is over here, we're kind of So what people actually care about when they're talking about the atmospheres, they don't really care so much about how much heat transport is. What you actually care about is what the profile of temperature is. So you're approaching the problem in a different way. But then you might want to know, well, how far apart are the clouds? How far away are the plumes? And you need to know whether it's going to rain or not. That's probably the most. So what's important then is condensation. Radiation is important because it's set up, and there's lots of complications. Okay, so as I mentioned, Rainy-Benard is the simplest addition to Rayleigh-Benard that includes moisture. So here are the equations. First equation, they should look familiar to you, and anything that's slightly unfamiliar will be in red. So momentum equation, mass continuity equation, it's incompressible fluid. There's a buoyancy equation. In addition to that, we add an equation for a condensate, I'll call it Q, which is diffused. And that's how it gets in, diffusion from the bottom. And this C sub Q is condenses out when it reaches saturation. And when it condenses out, it releases latent heat, enthalpy of vaporization. And so there's a heat source, a buoyancy source in this equation, gamma Q, and gamma is a bit like a latent heat of condensation. And then when does it actually condense? It condenses when it exceeds a saturation value. When Q is greater than QS, the saturation value, then all of it, all the excess immediately falls out. So it immediately falls out in an idealization, and that is rain. And so we model that. H here is a Heaviside function. So only when Q is bigger than QS, then it condenses rapidly, tau is of very small number. And
So it never evaporates again?
not in this model. Not in this model. That would be the next step up, if you will. But in reality, the rain falls and then some of it evaporates again on the way down. Yeah. But I just, well, in the interest of staying close to Rayleigh-Benard, yeah.
You might have said it, but I missed it. What is Q exactly?
Q is specific humidity. It's a tracer, which is the amount of water vapor in the atmosphere.
Kind of concentration.
Concentration.
Perfect.
Concentration. That's right. Concentration. And it cannot exceed a certain value QS, which is determined by the Clausius-Clapeyron equation. Clausius-Clapeyron equation is an approximate exponential, the solution of it. So QS increases approximately exponentially with temperature. Temperature is not quite the same as buoyancy in an ideal gas, because temperature always falls off as you go up. Buoyancy will not necessarily fall off as you go up. That is what determines the stability. But the temperature is related to the buoyancy. This expression T equals B, buoyancy minus beta Z. Beta is what I'm saying, meteorologists call the dry adiabatic lapse rate. So temperature is really, and that, because buoyancy is basically density. We need to convert that to a temperature, and there's basically a linear conversion factor, beta equals G minus CP. So QS is exponential of alpha T, alpha, and beta. You can estimate what the value should be by looking at the properties of an ideal gas. But for the purpose of this talk, we'll just regard them as parameters, and we'll explore the behavior of the system with respect to.
Excuse me, I'm lost about the beta Z. I mean, doesn't the temperature depend on how the flow is? How the flow goes?
Yes, but it
Because-
will, of course. I mean, because B depends upon how the flow is. But if we know what B is, we know what temperature is through this relationship. And it's just a matter of a parcel of air, as it moves up, it will conserve its buoyancy. Buoyancy is a Lagrange conserves here, but an ideal gas won't conserve its temperature because it will expand. And as it expands, it will cool. So if it rises adiabatically, it conserves its buoyancy, but it expands and it cools. So temperature is not a Lagrangian conserved quantity, and it's related approximately linearly in an ideal gas. So temperature is B minus beta Z. And you can relate all this to an ideal gas. If the buoyancy of the fluid is minus G delta rho over rho naught in a Boussinesque fluid, that's meteorologists relate this to something called potential temperature, which is the temperature including this expansion term, and we end up with this relationship. And T just comes into the problem through the Clausius-Clapeyron relationship, through determining what the saturated vapor pressure is when condensation occurs. And well, this is the actual Clausius-Clapeyron solution. And you end up with this approximation that the saturated concentration depends exponentially on this temperature, and this factor alpha depends upon various properties of the gas, L, the latency to condensation, R, specific gas constant to the moisture vapor, steam background temperature. And these factors alpha and beta determine the stability. And then we can non-dimensionalize in the usual way. And then if it's a dry Rayleigh-Benard, they're just three numbers. The aspect ratio, the Prandtl number, which is the ratio of the diffusivities, nu over kappa. In my universe, Prandtl number is always one. One fewer parameter. And the Rayleigh number, which is the ratio of a buoyancy force to a diffusive force. In the atmosphere, in the actual atmosphere, that's of the order of 10 to the 21. It's a big number. When we add moisture, there's a bunch of other parameters which end up, but a lot fewer than there are in the real atmosphere. There are things like a moist Rayleigh number, which is how much, it's the ratio of how much buoyancy the condensate releases when it evaporates, so the diffusive force on the bottom. That's similarly about the same order. Or equivalently, the ratio of the moist Rayleigh number to the actual Rayleigh number. But look at the atmosphere, the real atmosphere, that's about 1 typically. There's this dry adiabatic lapse rate, the beta parameter I talked about. And there's this alpha parameter, which appears in the Pascal graph. So this alpha, perhaps the three new non-dimensional numbers to think about this moist Rayleigh number and this beta parameter, difference in buoyancy and temperature, and the class is Clapeyron. Okay.
Just remind, what's the typical Rayleigh number in a lab if I did the experiment?
In a lab, still pretty big, and mainly the main difference is this H.
Yes.
So instead of 10 kilometers or 10,000 meters, maybe you've got 1 meter, depending on how big your lab is. So 1 to 10,000, what's that? 10 to the fourth. 10 to the fourth cubed is 10 to the 12th. So subtract 10 to the 12th from that, and you get 10 to the 9th would be a lab thing.
And critical Rayleigh numbers are.
Oh, a lot less than that, hundreds. I forget what they are, I should know this.
Remember?
You know this number when you're teaching it, 2,400 or something. A lot less. And I do lab experiments, I do computer experiments sometimes. And 10 to the 9th is actually a pretty good Rayleigh number for computation, for a computer experiment. And of course, if you ask a meteorologist, just an atmospheric scientist, you know, somebody who knows how the weather actually works, you ask them what the Rayleigh number is in the atmosphere. First off, they probably don't even think about the Rayleigh number, so they don't know what the Rayleigh number is. Then if you explain it to them, then you say, oh, it's infinite. Because nu and kappa are negligible. But and some fluid dynamicists. Anyway, I think I've probably explained what these are already. I don't need to go through them again. But alpha, beta, gamma, the latent of condensation capacity, most important. 3 new parameters. And of course, now we can imagine experiments going from dry to moist and back again and see what the behavior is. There's also ends up being a conserved quantity. That's the equation for buoyancy at the top. Second, for concentration, there's this condensation parameter which gets rid of the concentration but gives you buoyancy. You can add those two equations together and get a conserved quantity which is conserved even in the presence of condensation. We'll call that M. It's akin to what meteorologists call the moist static energy. And dm by dz essentially determines the stability of the column in the absence of diffusion. If dm by dz is positive or negative, the column will be stable, just as dB by dz determines the stability of a column in the absence of diffusion. When you raise a parcel, if it ends up being less dense in its surroundings, it keeps on going. And M is the analogy for that. Now, turns out that we can find an exact solution with this system, we can find an exact moist extension of Rayleigh's conductive solution, which is just a solution of no motion, but with diffusion in it. But we allow for condensation. So if you just have diffusion, the left hand one at the top, does that show up here? Yeah, okay, that's maybe a better pointer. We have a diffusion of concentration with this heaviside function on the right hand side, the diffusion of buoyancy with gamma on the right hand side, the latent heat. Add them together, this condensation term drops out, and this quantity B plus gamma Q is equal to 0. So a single equation, but it's not quite. So if that were just one variable, it would be very easy to solve. That's the Vallis conductive solution. You just get a linear solution. But now we have B plus gamma Q. But if it's just diffusing, the flow will be saturated. So Q is equal to QS, saturated value. And QS, well, it's a function of T, but we can relate that to B because they're related. So we end up with this function. That B plus gamma QS just going to be a linear function, P plus QZ. A linear function has no second derivative. And so B, solving for B, you get B equals P plus QZ minus gamma times its exponential function. And P and Q are given by the boundary conditions on the top and the bottom. And it's not an obvious solution. So when I first came across this, I solved it iteratively. And you get a solution. Then I was chatting to an applied mathematician friend of mine.
Can I ask you about you have the title drizzle solution?
Yeah.
That means it's not raining yet.
No, drizzle is very light rain.
So it's just at the edge of condensing,
It is condensing,
but not much more than that.
not much more than that.
Got it.
And it's condensing because moisture is coming in from the bottom, and as soon as it reaches saturation, it drizzles out. But the amount of rainfall is just proportional to the diffusion because there's no great storm going on. It's just diffusing in through molecular diffusion and then drizzling out. It's, I'm sure you've been to England and had the weather there. So that's what the drizzle solution. Yeah, so we called it the drizzle solution.
And there's no feedback then between.
There is a feedback in the sense that you still have to. I mean, these are the.
I think like feedback, like drag, droplets coming down. So there's
No,
nothing like that. So that's what. Okay,
that's right.
good. No, I got it.
So we get this. which I solved iteratively, which I'm on the applied side of applied mathematics. And Jack said to me, that sort of looks a bit like, might have an analytic solution. So I went away and found this solution, which is in fact, the actual solution turns out to be a special function, the Lambert W function, in an applied math department. So you've probably heard of it, even if you don't know what it is. And what it is, the Lambert W solution, without being too flippant, it is a function which is defined to be the solution of this equation. So, but it is, having said that, it does have a, if you know that it's a function, you can do things with it, you can differentiate it, and so on. And it was rediscovered in the 50s, actually. First, turns out it was first done by Euler in correspondence with Lambert, but Euler really. But the guys who rediscovered it from, I thought that Euler already had lots of things named after him, so they named this name. The Lambert W function. Anyway, but it, like many things, it's named after the second person to discover them. And then you actually get, this is the actual solution. Actually, I'll show you this solution. It's perhaps a little bit better. Here we're starting out with with unsaturated boundaries. So if it's unsaturated, both B and the concentration are diffusing independently of each other. So if they're diffusing, the second derivative is 0, so it's a linear function. So the blue curve here, the dashed part is just a straight line. And the buoyancy, Q, is also just diffusing. And so that's falling off. Then they will both diffuse, and at some value in the interior of the domain, the flow will become saturated. And then you will get this condensation, and it will no longer be a B and Q will no longer be a linear function. They won't diffuse independently. There's some B plus gamma Q in this line here, this green line, keeps on being a linear function. But Q, the red line, and the buoyancy, the blue line, then obey the solution, which is this Lambert W function. So, in a sense, what we've done then is we actually found an extension to the moist atmosphere, which is sort of an extension of Rayleigh's solution. But now we have this concentration. We have rain in it, and we call it the drizzle solution because the rainfall is very, very light. It's just so the actual form of this solution, which is here, depends upon alpha, this value in the Clausius-Clapeyron, and beta, the connection between temperature and buoyancy, and the boundary conditions determined by P and Q, doesn't actually depend upon the diffusion. So the actual solution doesn't depend upon the diffusion, but the amount of rainfall will, because that just as in the original Rayleigh's solution, this solution was just a line of temperature between top and bottom, determined by the boundary conditions. That solution itself doesn't depend upon the diffusivity. Of course, the amount of heat which is flowing up is proportional to kappa. So it's analogous here. And then we can start thinking about the actual stability of the flow. You'd have instability when dm by dz is less than 0, and m is it's just the extension of buoyancy diminishing with height, but m is the buoyancy plus gamma q. So this is the instability criterion in the absence of any diffusion in the infinite. And what we can do is just with a little bit of manipulation and non-dimensionalization, assume that we can non-dimensionalize such that the temperature between the top and the bottom is always -1. And then we get criteria for when it could be dry unstable, so unstable even in the absence of moisture, and that will be when this parameter beta is less than 1. But you can also find a regime when it's potentially dry stable but moist unstable, and that turns out to be when beta is greater than 1 and gamma is greater than beta minus 1, and to necessarily follow that so quickly. But the point being, you can find a regime when it's purely dry, unstable, just regular Rayleigh-Benard convection, or a regime when it would be stable if it were dry, but you had moisture, which destabilizes it because of this latent heat effect. I'll just show you a couple of, these actually have analogues in the meteorological community called the dry adiabatic lapse rate and the moist adiabatic lapse rate. And the dry adiabatic lapse rate is just, as I said, when dB by dz becomes negative, you convert that to a temperature criterion. And there's also something similar, highly complicated moist criterion. Okay. Then it turns out that by varying this value of beta, so here's a regime diagram. Beta was this lapse rate, gamma is the latent heat of condensation. Just by changing gamma, we can go from a state which is, again, in the absence of diffusion, purely stable, then dry stable but moist unstable, or completely unstable. So we can then look to see what the different behavior of the system is in its criteria. And also, Ben Brown and Geoff Vallis were able to actually solve the eigenvalue problem. Now, this was done by, well, Rayleigh and then Chandrasekhar for the dry problem. When you add moisture, it is, as far as I know, impossible to do it analytically for the moist problem. But Ben and Geoff were able to do an eigenvalue for the moist problem. This is just the instability properties in a purely dry case for different values of Rayleigh number. As you increase the Rayleigh number, it becomes unstable at a particular weight number when the Rayleigh number is high enough. Now add moisture to it. It looks actually relatively similar if you normalize things appropriately. Here they've looked at what the growth rate is and it's unstable for quite a lot of parameters around a particular wave number. The solid lines are for cases which are dry stable, or moist unstable. The dashed lines are dry unstable. But you end up with a peak at around some particular wave number, which is the most unstable. So you might expect, if the linear problem maintains itself as you go into a nonlinear regime, you would have some kind of spectral flow. In fact, if you do the numerical simulation, so this is now a fully nonlinear three-dimensional simulation, and done by Chris Howland. And as you go from beta equals 0, which is dry unstable, to beta equals 2, which is would be stable if it were dry, but it's unstable because of the presence of moisture. You actually get very different behavior in the moist case, and that's clearest perhaps in the bottom panel. So dry unstable gives you this the main filling convection on the left. But as you go to a dry stable case, but moist unstable, all of the convection and this simulation concentrates itself into a single plume. And let's skip that. And here are some typical types of numerical simulations. I'll show you a couple of movies in a minute. At a relatively low Rayleigh number, 2 times 10 to the 5th, you get these sharp plumes, finite number of plumes. As you increase the Rayleigh number, the number of plumes diminishes. Finally, in the top row, they're all steady solutions. In the bottom row, they become unstable and they're going all over the place. I'll show you.
These are in a periodic box.
It's in a periodic box. Yeah, that's right. And this is just showing you the onset from a localized perturbation. Hopefully the movie will work. Did earlier. So it's an unstable setup. The fields at the top are buoyancy, concentration of moisture, temperature, and the velocity field. And you can see here on the second that we just made a small perturbation in the concentration field to make it saturated there, so it's going to condense there. And what will happen is that this will grow, it will give you an updraft, then waves will propagate away from it, they will perturb it elsewhere, and you will get polar updrafts. So just look at, say, the top figure. Bang, 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 bang. And then, that's kind of it. I'll play this again. And it stops there. But what's interesting is that, well, it perturbs the system, you get many plumes. But then there's, you have too many. And each plume is drawing moisture in from the boundary where it's, and so they're drying out the region away from it. So the plumes next door is starved of moisture. So it will. So initially you get many plumes, and then the plumes merge. So I think it's most easily seen on the top panel. First of all, you get about a dozen plumes. Then some die away. The stronger ones survive, and here we are ending up with 5. And it's sort of analogous to hurricanes. You can't actually have too many hurricanes in the Atlantic at the same time because they're starving each other of moisture. Some relative humidity snapshots.
I'm just curious. So the plumes merge, and so at first I thought, okay, that would eventually mean that you end up just with one plume. Is
Yeah.
that
Yeah, well, you might, well, not in this simulation. Not in this simulation. I mean,
asymptotically, it remains to be a periodic array of plumes?
Not numerically, at least. Let me not. Yeah, it ends up being an array of plumes. But if, for example, if we went back to this figure here, in this simulation, there is just one plume. So that will depend upon very much on what the parameters of the system are, as to how much, you know, if it's very unstable, if this is very hot, and that's very cold, you know, your plumes will be more intense and they will be drying. You know, they'll be drying things out here. So it depends on how big the domain is and also how intense this is, because we've also got moisture coming in from here. So if these aren't all that intense, we can get another plume here because it's moist enough. But if it's very intense, the plume separation will be larger. Now, it would be nice to know, to have a theory for that, not just a verbal hand wavy thing. But I think it contains, and you can see here in that top plot, before it's gone wildly unstable, as we've increased the Rayleigh number, the number of plumes has diminished from 5 to 3. Here we've increased the Rayleigh number by a factor of 10. So basically now I'm going to show you a bunch of movies. This shows you some strong updrafts. Also, in this simulation, turned out we would also get downdrafts from the top, because if just you're not very moist up here, and this is cold, you can actually get unstable downdrafts from the top. It's probably not a realistic aspect of the simulation. This is a horizontal slice near the bottom in a 3D simulation, as labeled vertical velocity, moisture, and buoyancy. See what happens. So initially, lots of tiny updrafts. Rayleigh number 10 to the 7th, so well into the unstable regime. Still maybe factor of 10 to the 14th, less than the atmosphere. I'll just show that again. So horizontal slice near the bottom. The red on the left panels are updrafts, lots of small updrafts, tiny ones, then merging, getting some other weird and wonderful patterns. And it's these patterns which were just now, when I say we, it's well, Chris Howland did these, and show you a few others in a minute. We had uniform, here we added some uniform cooling, mimic radiation, because one thing in the atmosphere, or one thing is when flow is coming down, it's getting warmer. The only way it can come down is if it's balanced by diffusion. So the balance is between the vertical advection and the diffusion, which is probably not realistic in the real atmosphere if we think that the diffusion is very small. So we can add a cooling and again get very strong updrafts now disappearing as they approach the top layer. The relative humidity, which is Q divided by the saturation value, tends to have a maximum in the middle. You get this relative humidity, oh sorry, a minimum in the middle. Relative humidity is Q divided by QS. So your humidity divided by the saturation value of the humidity. It's largest at the top because it's largest at the bottom because you've got a very wet surface at the bottom, bringing it in. Very little moisture at the top. And the moisture gets dragged up in very narrow plumes and comes down, very little moisture at the top. It's coming down in broader areas. So if you average the humidity, just an unweighted average over this, you'll find quite high values of relative humidity here, but never exceeds 1. Low values of relative humidity here. Yeah, fluid coming down, it's dry. So you end up with a minimum values of relative humidity in the middle. Skip a couple. And let me just finish with some movies. It's a very rich system. Here's a non-rotating one. And this more or less keeps going the way it is here with about 4 updrafts, but there. No, it's good. Not fewer, now 2. Wonderful patterns, as yet unexplained. Here's one from Whitney Powers. Whitney graciously gave me this movie. She is a grad student at CU. She's non-rotating. It's a horizontal slice near the middle. Rotating. So now there's some other non-dimensional parameters, the rate of rotation, measured by the Ekman number. So this is a moderate rotation, say. They're pretty. All of these now, all of the little vortices on the left are little hurricanes rotating the same way. With rotation, Ekman number smaller, it actually condenses into this little crystalline state. It just stays there for as long as we can tell. 1, 2, 3, little hexagons. So it's tiled with hexagons. So I think, in a sense, what I've done is I've provided you lots of new results, presented a system which has got very rich solutions, very rich numerical solutions, which are getting a little bit more towards the real atmosphere, and we'd like to understand more of it. Some problems seem approachable. I don't know whether an analytic solution, linear stability solution of the drizzle state is possible. I can't imagine how. Maybe we don't need an analytic solution anymore. We've got eigenvalue solvers and so on. But a bunch of other unsolved problems. You know, the transition to turbulence in Rayleigh-Benard goes through now a well-defined or reasonably well understood sequence of period doublings and so forth. I don't know whether that's the same for the moist system or whether it just explodes all of a sudden. There are various quote unquote upper bound theories in Rayleigh-Benard convection that we know how much the heat transport can be. But there's still arguments about this ultimate regime. And I think one thing that actually puzzles me is that I think, I suspect that, well, I would like to think that the transition to turbulence goes through a subcritical bifurcation, meaning, which means in practice that you can maintain the turbulent state even when it's linearly stable, because once it's in this turbulent state, it's always providing finite sized perturbations which are creating more turbulence, and so it's self-sustaining. I've actually never seen, I mean, we have examples in fluid dynamics, or solid flow type, which is linearly stable, but can be turbulent. I kind of think that this system should be like that, but we haven't been able to find that. And I think that's about it. I'll just stop here. Thanks.
Thanks, Geoff. We have a few minutes for questions. Any more questions?
Yeah.
So you drew your line between clouds and the Rayleigh-Benard system and said you're here.
Yeah.
I guess my question is, are there either experimental or observational situations that are here that you are comparing with, or what do you think? How much further do you think you need to move this direction?
Oh, towards reality.
Yeah.
Here we are. Right, it's for you. Path to realism. There's many things which are, a meteorologist would say, okay, you're
Cute.
so yeah, they'll say, yeah. Good job, Geoff, but as somebody mentioned, when it rains, quite a lot of the rain actually re-evaporates and becomes cold. We could put that into the model. I mean, you're just headed towards more and more numerical. That path to a purely numerical, possibly a lab experiment. So liquid water clouds, which then affects the heating and cooling through radiation. So I think it's this first bullet point, I think, is sort of see, most actual simulations of atmospheric convection, I mean, they have their own problems too. They may have some of these things in like liquid water and clouds and radiation, but they also typically have turbulent parameterizations for the boundary layer. They ramp up the viscosity in the boundary layer according to some formula that they like to think of. So, they're very ad hoc. They're a long way from doing DNS. So, but I think I would like to put in some of these things. We already have some aspects of radiation, liquid water too. So, but then it's, once you're in the real system, it's very hard to do lab experiments. Well, it's hardly any system to do lab experiments because your Rayleigh number is so much smaller than reality.
I mean, is anybody doing experiments that are close to this?
It's hard to do. I don't know anybody doing lab experiments which are close to this. No.
Miguel Lebels, one of my collaborators in France, has something which is kind of similar to some aspects of this. I mean, it's not exactly this model, but it has some of the same ingredients.
Yeah, I mean, I'm also wondering, like, with your pretty patterns, you know.
Yeah,
Do any of the pretty patterns look like they may, like that you may be capturing the dominant things that are going on in some system?
Yeah, I mean, I think, you know, you do see patterns in clouds. I mean, if you look at some satellite photographs of big cloudy areas, I don't know whether you see anything quite as pretty as this, or quite as regular as that, but you do see. And also, I mean, just in ordinary Rayleigh-Benard convection, people have seen things like hexagonal flows in some convective aspects of it. So I think that's, I mean, in a way, you put your nub on the problem, which is that to be realistic, you're probably a long way from understanding the system in any way that say, an applied mathematician or a theoretical physicist thinks of as understanding your, even your numerical simulations are not in the right parameter regime. So you can understand there was a quote I heard, people like to explain famous. They would say, as so-and-so said, it's a famous person, because they get kudos. So, but Joe Callas apparently said, if you come across a problem that's too difficult to solve, simplify it until you can solve it. So that's sort of the path we've taken here, is to start with something relatively simple. Yeah.
When I think of, I guess we should call it the dry Rayleigh-Benard, you think these nice cells.
Yeah.
Before, of course, it's turbulent. And here you got nice cells, but you have to add rotation to it. You ever get
Yeah, it's true.
a nice cell like that when you don't have that rotation?
I haven't not seen that, no. Not seen that.
So the rotation is necessary to get this well defined.
Seems to be, yeah, to get these crystalline states. Yeah, you're right.
And then the other question is, the updraft is much stronger than down.
Yeah.
What, and why is that?
Oh, that's because here, this fluid is getting colder. It's condensing, releasing heat, which is a new buoyancy source for the updraft. So you get a positive feedback. Whereas when you're coming down, you've got dry air coming down. There's no such positive feedback. So that is and that is what we see. If you actually go out into a heavy cumulonimbus storm and get into the updraft, you can be whisked up at about 10 meters per second. If you're not careful.
So I'm so just to, maybe I'm being dense. So that's because the humidity that could evaporate actually has fallen down.
Oh,
Because I mean, if the humidity stayed, you know, the condensed stuff stayed up there,
yeah.
it would evaporate and would
It's
undo
true,
the
you
same
could-
thing. Is that
potentially you
because
could
it
get
rained down?
Potentially you could get that, but in reality, it's also the case. I mean, in fact, you know, in these updrafts, you get pretty hefty condensation. The raindrops forms are pretty big. So a lot of the rainfall does actually come all the way down. So a lot of it has gone. So even if we were to add this system, it would still be the case that the subdraft would be a lot stronger than the downdraft. So that's why we omitted it. We figured that's a complication.
Yeah, I think that's all the time we have, so let's thank Geoff again.